Okay, back to recording in progress. And let's see. Okay, so we were looking at integral from 0 to 1 of sine of x to the fourth dx with an accuracy of 0.0001. All right, so I start off with the formula for sine of x to the 1 over 1 factorial minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial plus dot, dot, dot. So just like any other function, sine of x to the fourth, right here, right here, right here, right here, erase the x and put parentheses x to the fourth to the first, x to the fourth cubed, x to the fourth to the fifth, x to the fourth to the seventh. So it becomes x to the fourth over 1 factorial, which is 1, minus 1/6 x to the 12th, plus 1 over 120 x to the 20th, minus 1 over 7 factorial is 5040 x to the 28th dx. Okay, this is x to the fifth over 5. This is 1/6 x to the 13 over 13, 1 over 120 x to the 21 over 21, and so on. 1 over 5040 x to the 29 over 29. So there it is. So x to the fifth over 5 minus 1/6 x to the 13 over 13 plus 1 over 120 x to the 21 over 21 minus 1 over 5040 x to the 29 over 29 plus dot, dot, dot. Even though there's infinitely many terms, when you plug in 0, you get 0. Plug in 1, all the numerators are 1. 1/5 minus 1 over 6 times 13, 78, plus 1 over 120 times 21 is 1 over 2520, minus 1 over that times that, which is 146,000 whatever. Okay, this is an alternating series. Terms decrease in absolute value and they approach 0. Therefore, the series converges by the alternating series test. And if we stop anywhere, the error is no more than the next term. The original question, you want an accuracy to within 0.0001, 10 to the minus 4. This is already less than 1 in 10,000. So just add up these. Okay, so add these 3 on your calculator, round to the nearest 0.0001, so 0.1876 is my answer. Okay. So keep in mind, you're supposed to add up infinitely many terms. I've only added up 3 terms. That's okay. The error is no more than 0.0001. So the true value we're going to state is 0.1876. And we know for sure that it's between 0.1875 and 0.1877. And in case you say that's not good enough accuracy, well, you can go more terms, right? The more terms you have, the greater the accuracy that you have. Okay. All right, so that's what we have over there. Okay, then the last thing we have are a couple of limits, 61 and 63. Use series to evaluate the limit. And then once I have that, I think I'm done with the section. Unless anybody has any questions, I'll introduce the last section and then we're going to quit after that. Okay, so 61. It used to be 55. Limit x approaches 0 of x minus ln parentheses 1 plus x over x squared. Okay, for 1 over 1 plus x, you can always derive that by treating that as 1 over 1 minus negative x. So that's a geometric series where the first term is 1. Common ratio is negative x. So 1 minus x plus x squared minus x cubed plus x to the fourth and so on. And then if I integrate that, which means I'm going to integrate ln 1 plus x. Okay. C plus x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 plus x to the 5th over 5, and so on. Okay. So this we saw before was ln 1 plus x. Okay, so c plus x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 plus x to the 5th over 5, and so on. Okay, then you can plug in 0. If you plug in 0, these are all 0. Then that gives me c is 0. Okay, so in other words, here's the expansion for ln 1 plus x. Okay, x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 plus x to the 5th over 5. And you might recall that's how we got the formula for natural log of 2. If I plugged in 1 plus 1 is 2, 1 minus a half plus a third minus a fourth plus a fifth. That was our famous alternating harmonic series, you might recall. Okay. Then getting back to our problem, x minus ln 1 plus x. Whoops, try to get this into focus. X minus ln 1 plus x. Okay. So x minus this whole thing, right? Now, if I'm going to go x minus this whole thing, that's going to drop out. Each of these signs will change, right? Imagine it's x minus parentheses. Okay, so that's going to be gone. And then there'll be a minus in front of the whole thing. So I change all these signs. So x squared over 2 minus x cubed over 3 plus x to the 4th over 4 minus x to the 5th over 5. And divide all that by x squared. Okay, so if I divide by x squared, that just becomes 1. That becomes x squared, x cubed. Okay, so here's the power series expansion. X minus ln 1 plus x over x squared is 1/2 minus x over 3 plus x squared over 4 minus x cubed over 5 plus dot, dot, dot. Okay, so now limit as x approaches 0, which was what the original question was about. Limit as x approaches 0 of x minus ln 1 plus x over x squared is the limit as x approaches 0 of this stuff. Okay. Even though there's infinitely many terms, all of these are 0, right? 0, 0, 0. They all drop out. So the final answer is just going to be 1/2. So there we go. Okay, finally 63. Limit x approaches 0, sine x minus x plus 1/6 x cubed divided by x to the 5th. Okay, sine x, you've got that on your cheat sheet. You're allowed to have this for the test. X minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Okay. And a side note, mentioned that looks exactly the same as inverse tangent, except no factorials here, right? Factorials here, otherwise identical. Okay, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot, dot, dot. All of that minus x plus 1/6 x cubed. Okay. That cancels that. This is negative 1/6 x cubed, right? 3 factorial 6, negative 1/6 x cubed plus 1/6 x cubed. These are gone. So I have this one, infinitely many terms after that. Okay. You say, what about writing the 4 terms? You could write more, but in this case, you don't have to because you're not really writing the terms out. You're just trying to find the limit. Now, if I divide by x to the fifth, that x to the fifth divided by x to the fifth gives me 1 over 5 factorial. Divide that by x to the fifth, that'll be x squared over 7 factorial, plus dot, dot, dot. All the rest of the infinitely many terms are going to have some x's, right? If I were to write more, it'd be what? X to the 9, 11, 13. If I divide by x to the fifth, there's still going to be some kind of x, right? X to the 9th divided by x to the fifth would be x to the 4th. The next one would be what? X to the 11th divided by x to the 5th is x to the 6th. We don't care what they look like. They're all going to have some x. So now I have limit x approaches 0 of 1 over 5 factorial. Okay, that's gone. That's gone. That's going to be minus x squared over 7 factorial plus a bunch of terms that all have an x, which means these will all drop out. All of these drop out. The only non-zero term is the first term. So 1 over 5 factorial. Final answer, 1 over 120. Okay. All right, folks, I'm going to now mark off (11:10), and believe it or not, we're down to our last section of Calc 2. Okay, so we're pretty close to being done. 11.11. I don't think it's even that much of a new section except for the Taylor's inequality that I'll talk about. So I'm going to give you an introduction to it. Show you what's up in this section. (11.11) Taylor polynomials. These are actually polynomials now. Okay. Formula for Taylor series. If we stop somewhere, if we stop at the nth derivative exponent and factorial, we really have a polynomial. So instead of going to infinity, we stop at n. So notice this looks exactly like the formula for the Taylor series. The only difference is it doesn't go dot, dot, dot at the end. This is degree 1, 2, 3, 4, 5, whatever. Okay. So a lot of what happens in this section is we're going to stop. So instead of going on forever, we approximate with the nth degree Taylor polynomial. Okay. Just a side note, you can see some of this on a calculator. So figure 1. Excuse me. Go back to this. E to the x. We can approximate with 1 degree 0, degree 1, 1 plus x. By the way, you did a lot of that in Calc 1, right? Calc 1, find the equations of the tangent to the curve, right, at a certain point. Linear approximation. Now we can do quadratic approximation, cubic approximation, 4th degree, 5th degree. As you take more and more terms, the graph looks more and more and more like e to the x. Okay, so look at the picture, page 774. Okay, the red is e to the x. T1, that means Taylor polynomial degree 1. That's y equals 1 plus x, 1 plus x. That was the graph that you did a lot of in Calc 1, the equation of the tangent to the curve, right? Remember, you did a lot of problems. Find the equation of the tangent to the curve, blah, 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 at the point. Okay, but now T2, parabolic approximation. T3, cubic approximation. You go farther and farther and farther out, the graph looks more and more and more like the graph of the function. Okay, that's what's happening. Page 777, figure 6. Okay, I don't have any more hands because I have to hold up the book. But the red graph is the sine function. See the sine function? T1 is the tangent line. It happens to be y equals x. The best linear approximation to the sine function near the origin is y equal x, right? And if you take a look at this, it looks pretty good for only a little while. Then they're showing you x minus x cubed over 3 factorial. That's T3. Then x minus x cubed over 3 factorial plus x to the fifth over 5 factorial. That's T5. Here's T7. As you go farther and farther out, the graph looks more and more like the sine function. Okay. Just for fun one time, I actually went all the way out to the 99th term. So I went all the way out to what? X to the 99 over 99 factorial and graphed it. Okay. It looked almost exactly like the sine function for maybe 3 or 4 periods. Okay. And then of course, farther on, you know, in the long run, it doesn't look like it. Okay. But if you go infinitely far, you essentially have the sine function. Okay, the approximation gets better and better and better. Right, so what's happening in this section? Uh, 1 to 9, 13 to 21, which is not really that many problems. So let me show you the problems for those who don't have the book and aren't getting it again. For one last time, page 780. Sorry, I got to raise up the book. Okay. Find the polynomial T3, third Taylor approximation. T3 means you're going to write down 4 terms, the constant, x, x squared, x cubed. So you're essentially doing the same thing as before, except you're not putting dot, dot, dot at the end. Whoops. And then 9. Okay. The new stuff is how good is my approximation if I do not have an alternating series. So that takes you all the way up to problem 21. Looks like. That's where we have to use this Taylor's inequality. Page 775. And I will replace this right over here. If you had to memorize it, this is much easier to memorize. If you stop after n terms, the remainder is no more than the n plus first derivative, exponent, and factorial in absolute value. You see how it goes absolute value of fn plus 1 of x less than or equal to m? Just put this over here. There's an upper bound for that. Okay, so this is really the n plus first derivative, exponent, factorial. That kind of goes along with the alternating series test. If you stop anywhere, the error is no more than the next term. So similarly, the same vein here, the error is no more than the next n plus first derivative, exponent, and factorial. And I'll show you how that works. Okay, I was just going to show you one problem, which is not even in our book. It was in the previous edition. So I'm calling it 3 star, I guess. Yeah, because they changed it up on me. Well, it looks like it might be a little bit like 13. But on the second thought, it isn't. It's set at a different point. It is 1 over x, but the a is 2. So anyway, I'll just call it 3 star. Go from there. Okay, f of x is 1 over x, a equals 2. The directions say find the Taylor polynomial T3, which means you need the first derivative, second derivative, third derivative. That's exactly what we were doing anyway, because we're holding to our rule of having at least 4 terms. Just before, we were putting dot, dot, dot. No, you're not putting dot, dot, dot. So I'll do that to me. All right, so find the third Taylor polynomial, which approximates 1 over x at a centered at a equals 2. And by the way, here's another reason why you can't just say, let me always center at a equals 0. You're not allowed to plug in 0. Okay, now here's the way it always works. If you're centered at a equals 2, automatically, even before I start, x minus 2 to the 0 over 0 factorial. X minus 2 to the 1 over 1 factorial. X minus 2 squared over 2 factorial. X minus 1 cubed over 3 factorial. Before we said plus dot, dot, dot. Now we're not going to put the dot, 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 because we just want a true polynomial, a true cubic. This is the best cubic approximation to this function near x equals 2. In Calc 1, all you did was the tangent line, first degree approximation. What's the best straight line approximation to the function near blah, 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 right? Okay, so here's the function, x at -1. F prime is negative x at -2. Double prime, 2x at -3. Triple prime is -6x at -4. This is better for calculus, but this is better for algebra. And now, since you're centered at 2, you don't plug in 0, you plug in 2. Wherever you're centered, that's where you plug in to the function, the derivative, second derivative, third derivative, and so on. Okay, f of 2 is a half. F prime of 2 is -1/4. F double prime is 2 over 8, which is 1/4. And triple prime is -6 over 16, which reduces to -3/8. So EF, exponent factorial. And the derivatives go right here. 1/2 goes there. -1/4 goes there. 1/4 goes there. -3/8 goes there. And then we just clean it up. Okay, yes, this is 1, this is 1. So 1/2 -1/4 x minus 2 to the first power. Slide the 4 down with the 2, that gives me 1/8. So 1/8 x minus 2 squared. Slide the 8 down, that's -3 over 8 times 6. So that's what, -3 over 48, which reduces to -1/16 x minus 2 cubed. Okay, stop, no need for dot, dot, dot. So this is the best third degree approximation to this function near a equals 2. Okay, so that's as much as I'm going to show you today. So sorry, I had to break up into 2 different videos, so I may be sending 2 videos today, but that's okay, be that as it may. Okay, so I'm done with 11:10. All we have is 11:11 left for the remaining time. And last exam is Thursday the 9th, and then our final exam will be on the 17th. Okay, so let me stop and see if there's any questions in the chat. If not, we're finished, folks. Okay. Any questions, please? All right, so that's about it. And have a good day, and we'll see everybody next time. Okay. All right, bye, everybody.
All right, take care, Professor.
Thank you.